Welcome, my dear university students and YouTube viewers, to Chapter 5's continuing coverage of thermochemistry. In this video, I will teach you enthalpy of formation. So what are enthalpies of formation? Well, we can use Hess's law, which I discussed in a prior video linked to in the description below and floating above my head here, to calculate a compound's enthalpy of formation, which is also called its heat of formation, or delta H sub F. Now, to do this, you have to use tabulated delta H data, which you can Google or something, or you can find in Appendix C on these pages of the text that I recommend for this class, which is Chemistry, the Central Science, 12th edition. Now, these delta H sub F values in Appendix C tell us the delta H's of making each listed substance from its parent elements. For example, the listed delta H sub F for propane gas, which has this formula, is negative 103.85 kJs per mole. What does this mean? Well, this means that if you make 1 mole of C3H8 from its parent elements in their elemental state, hydrogen, carbon, then that process is going to expel 103.85 kilojoules. Make sense? The balanced chemical equation then would look like this. I have 1 mole, hence the coefficient of 1, not written but implied, of C3H8 product being formed from its elements, carbon and hydrogen. And I have to balance this however I have to balance this. Again, the delta H for this reaction, or delta H of formation of 1 mole of C3H8 is negative 103.85 kJs. Cool? Now, this also means that the reverse of this reaction has the exact same value, but the opposite sign, as I also stated in our prior video. If you reverse products for reactants, reactants for products, that is, I take this equation and flip it, the sign of the delta H changes. So if I took C3H8 and broke it apart into its parent elements, carbon solid and hydrogen gas, it would require an investment of positive 103.85 kJs. Now, I have to reemphasize, because this is important, the enthalpy of formation is the delta H of the chemical reaction of forming 1 mole, not 2, not 3, not a half a mole. It's 1 mole of a single substance from its parent elements, specifically at 298 kelvins, which is 25 degrees Celsius, around room temperature, and 1 atmosphere. These specific conditions. Now, in case any of you care, these conditions, called standard state conditions, are not the same as STP, standard temperature pressure. Those are two different things. I talk about STP in a later video that I've linked to in the description below and is floating over my head if you care. For example, H2O is made from 2 parent elements, hydrogen and oxygen. Because these 2 elements are diatomic, and if you don't remember what diatomic elements are, please click the link in the description below, as well as floating over my head here. In their elemental forms, hydrogen's formula is H2 and oxygen's is O2. It's not H and it's not O. Thus, the chemical reaction of forming 1 mole of H2O from its parent elements looks like this. You write H2O as a product, and you write H2 and O2, the parent elements in their elemental diatomic states, on the left. Now, to make this reaction be completely correct, we have to add the physical states of each substance at 25 degrees Celsius and 1 atmosphere. This is around room temperature and normal pressure. Now, what condition, solid, liquid, or gas, is H2 at room temperature? Yeah, it's a gas. And what about oxygen? Yeah, it's also a gas. And what about H2O? Yeah, it's a liquid. So I'm going to add these physical states right here. Gas, gas, and liquid. In addition to this, we have to balance the equation. Now, in order to balance this equation while keeping a 1 or 1 mole coefficient in front of the H2O, we actually end up having to use a fraction coefficient next to the O2. Now, remember, when you're writing out equations that are standard enthalpies of formation, you have to keep a 1 coefficient in your product on the right. Has to be a 1. Now, this means that sometimes, in order to achieve this, you do have to use fractions as coefficients for your reactants, which we're not typically accustomed to, but we do have to do in this specific scenario. Now, before going on, it might be beneficial for me to show you a periodic table that illustrates what the physical state, solid, liquid, or gas, is of every element. At 25 degrees Celsius and 1 atmosphere pressure, every single element in its elemental state is a solid, except for the green-colored ones here. These are gases. And the 2 unusual elements, bromine in its elemental state, because it's diatomic, has a formula of Br2 and is a liquid. And it's a smelly, awful liquid. And mercury is also a liquid. These are the 2 very unusual elements. They happen to be liquids. All the green-colored ones here are gases, and everything else is a solid. Now, the dark blue ones here, including technetium and these other kind of higher atomic weight elements, are all synthetics and sometimes only exist in such tiny quantities that we aren't completely certain if they're gas, liquid, or solid. All right? I urge you, my students, to please commit this to memory. Again, mercury and bromine, liquids, these other substances over here, they're green gases, and pretty much everything else is solid. With that in place, it should make sense why we have to write H2 gas, O2 gas, and we're dealing with H2O liquid here in this case, although you can also write a separate equation with different values for H2O gas or H2O solid. Now, because this balanced equation represents the chemical reaction of forming 1 mole of H2O liquid from its parent elements under standard conditions, 25C in 1 atmosphere, the delta H for this reaction is the enthalpy of formation for liquid H2O. And it happens to come to negative 286 kJs per mole. Now, as I also taught you in a prior video linked to in the description below and floating over my head here, the delta H for any transformation or reaction, that is the delta H for reaction, can be calculated as the total sum of all the enthalpies of your products minus that of your reactants, or better said, H final minus H initial. Now, this equation can be rewritten in a more technically correct way as follows. Delta H for a reaction is equal to this minus that, where these little Greek letters sigma represent the sum of and the sum of. In other words, the total delta H for a reaction is equal to the sum of all of the individual H's for the products minus that of the reactants. Now, the letters N here represent the total number of moles or coefficients in the balanced equation that we have to use as a multiplier in order to arrive at that eventual sum. That is a very valuable equation that we'll use later on. Now, there's something else that you need to know about enthalpy of formation under standard conditions, which is what this little degree sign represents. So the enthalpy of formation, or delta H sub F, of any element in its standard state is 0 kJs per mole. What does this mean? Well, I ask you, at 298 kelvins and 1 atmosphere, in what state, solid, liquid, or gas, is H2? Yeah, as you just learned, it's a gas. This means that the delta H of formation at standard conditions, this little degree sign, of H2 gas is 0. Now, separately, the delta H of formation under standard conditions of H2 liquid or H2 solid is not 0. Now, this is true just of H2 gas, because gas is the standard state of H2 at 298 kelvins around room temperature and 1 atmosphere. The same is true of any other element. The enthalpy of formation, or delta H sub F, at standard conditions of any of these elements in their standard state, solid, liquid, or gas, is 0 kJs per mole. Now again, please do not confuse standard state, 298 kelvins in 1 atmosphere, with standard temperature pressure, or STP, which is 0 degrees Celsius and 1 atmosphere that I talk about in a later video. All right, as an example, I ask you, what is the enthalpy of formation, or delta H sub F, of each of the following? Yeah, as you can see, each of these are elements, that is, formula of either a single atom or 2 atoms for diatomics, and they happen to all be in their physical states, solid, liquid, or gas, at room temperature. This means that the delta H of formation for each of these substances at standard conditions is 0. Make sense? Good.